So in some strict sense, a lattice is an additive subgroup of the real numbers in n dimensions. This definition is not necessarily the most useful thing, so almost exclusively I'm going to work with the definition that a lattice is represented by a basis vector in n-dimensional space. So we use lambda to denote the lattice itself, and a basis vector is g1, g2 up to gn, and those are column vectors. And so then a lattice point, x, is an integral linear combination of the basis vectors. So a lattice point x is g1 times b1 plus g2 b2 dot 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 up to gn bn, where these b's are integers. So we only allow integer combinations. So we have a picture on the right-hand side of a two-dimensional lattice. You can see that there's two generator vectors, g1 and g2. It's very convenient to represent the lattice generator vectors in a matrix form. So that's an n by n matrix. We put the generator vectors in columns, so that a lattice point x is equal to the generator matrix G times B, where B is a vector of integers. So B is an element of Z sup n, which is the set of all possible integer vectors. Okay, so here's an example. If we take B is equal to the integer vector 0, 0, then x is equal to G times B. Well, 0 times anything will be 0, and we get that 0 is a lattice point. So we always have the case that 0 is a lattice point. Here's a second example. Take B is equal to 3 minus 1. Then x is equal to G times B. We can perform the multiplication, and we find that x is equal to 3 and 0.5. So that's this point over here, 3 and 0.5. So we've been drawing pictures in 2 dimensions. We'll do that a lot. And we showed the arrangement of spheres and pool balls. That's a 3-dimensional lattice. We can let the dimension get bigger, 4, 5, 6, 100, 1000, as big as you like. These lattices exist as mathematical objects, just we can't draw these lattices in n dimensions when n is higher than 3. Okay, so don't be scared of n dimensions. If you've already seen a 7-4 Hamming code, the 7-4 Hamming code exists in 7 dimensions, and it's a projection into 4 dimensions. So it's a 4-dimensional subspace of 7 dimensions. So you shouldn't be scared at all. You can compute the volume of a cube in n dimensions. So if you have a square of side length m, what's the area of that square? It's m squared. And what if you have a cube with side length m? In 3 dimensions, that's m times m times m, or m cubed. Well, we just keep on going into 4 dimensions. You can have a 4-dimensional cube, and that would have volume m to the 4th. Similarly, you can compute the volume of a sphere in 1, 2, 3, 4, etc. dimensions. By the way, in n dimensions, we always say sphere. So even 3 dimensions, we have a sphere. 4 dimensions, we have a sphere. 5 dimensions, we have a sphere. In 2 dimensions, technically it's a circle, but we just have the habit of calling it a sphere. So if you see a circle, I might be calling it a sphere.